Hello everyone, welcome back to my daily coding series. Today is day 61 of Coding Every Day. So today I'm going to look at another 2D dynamic programming question. So let's just do the next one on the list, coin change 2. So I've done coin change 1, and I believe I remember how to solve it. So let's look at coin change 2. You are given an integer array coins representing coins of different denominations and an integer amount, which is our target. Return the number of distinct combinations that total up to amount. If it's possible to make up the amounts. Oh, impossible. Okay. So we either return the number of combinations or 0, and we have an unlimited amount of each coin. So coin change 1, I believe, was the minimum number of coins, and this one is the number of combinations. Okay, so here we have 1, 2, 3. So how is this different from combination sum? Because there's this other problem called combination sum, which you're given a target and you're given denominations, and you want to do all the combinations of how you can add up to it. So how is this different from each value in coins is unique? What is, oh, okay. So we can't have like two denominations of 2, for instance. Okay, so how is this different from, so my question is, well, I guess it's dynamic programming. So we're probably going to cache something or we have to store something in memory. A simple approach to this would be just store or just do every combination. And then if you get over 4, then just stop. And just every time you get 4, you can just add 1 to it. So that would be pretty simple to code. So if we look at this, so we start off with 0, and then we have the length of coin, many options. So in this case, 3. So we could take a 1, 2, or 3. That would bring us to 1, 2, 3. And from each of those, we can do the same thing. So here we could take a 1, 2, or 3. We could take a 1, 2, or 3. And we could take a 1, 2, or 3. That would bring us to 2, 3, 4. This would bring us to 3, 4, 5. And this would bring us to 4, 5, 6. Right. And then we can do it again. So for instance, 1, 2, 3. I'll just do it for these two. 4. So 5. Our target is 4. So actually, so our target is 4. So here we would say, okay, that's plus 1 combination, right? This combination. Here is 5, so we just, stop. We don't do anything because we know that no matter how many more coins we get, we'll never add up to 4. Same with this. This is another combination. So if we do, so the first one was 3, 1. This one is 2, 2. So this would be another one. So we do it here. So 1, 2, 3 would give us 4, 5, 6. And that would give us plus 1. And then these two would be beat. And then, yeah. So we know that, okay, so this is the brute force approach. So that would be pretty simple. So I'm noticing that there is definitely some repeated work. So we know, for instance, that this 2 right here, everything here is going to be the same as everything here. So we know once we're at 2, there is 2 combinations. So we could just remember that and say, okay, well, 2 has 2 combinations, so we know that this branch here has 2 combinations right here. This 3, so we've already encountered it here, we know it has 1 combination, so we'd say that's 1 combination, and 4, of course, is 1 combination. So here we would get 1, 2, 3, 4, 5, 6, 7 would be the answer. Okay. So it would be 7, but the problem with this, so like the very total is 7, but it's not really 7. And the reason for that is, for instance, if we go 1, 3, we're counting that as 1, but we're also counting 3, 1 as another one. So whenever there's a duplicate, we can't count that. So we can't count 1, 3 and 3, 1. So that's the problem I'm facing now, is how do we ensure that that won't happen? So I guess what we could think is like, all right, so when we get to this 2, we'd say maybe we could cache it as like, okay, we're at 2 and we've used a 2 coin. Whereas when we get to this 2, we're at 2 and we've used 2 1s. I don't know if we have to store that information. So my question is, what information do we have to store so that we don't do duplicates? So maybe we could store like the combination that we're at so far. So for instance, if we go 3, 1, then we know that the pair 3, 1 has 1 pair. And then when we get to 1, 3, we could see that that's already in our list. Yeah, I remember running into the same problem with combination sum, and the way I did it was just like sorted both of them, but I felt like that wasn't the right way. So we could cache these as our keys. So the combinations so far. So we know that if we have 4, this will be 1. And then, so 3, 1 would equal 4. So then we would say that 3, 1 is also 1. Then we'd get like 2, 2, that equals 4. So then we'd say that also equals 1. So then we could get maybe there's a more clever way to do it, because this doesn't really help us, because every combination would just be 1 and we'd still have to calculate every combination. So if we look at the case of this 2 and this 2, right? So this 2, so we know that this 2 results in 2 combinations. So if we take the coin 2, we know that there will be 2 combinations in here, or if we're at the value 2. So then it becomes, how many different ways can you arrive at the value 2? And here we see that there's 2. So then we would say that there's 4 combinations for all value 2. Because there's a combination where you just start with 2, and then there's a combination where you go 1, 1. We could also think of it like, so we could think of it like we used 1, 1 here, so we can't consider this 1, 1. But then that may give us complications. Okay, so maybe we could start with 4. We know, well, that's, if you're at the amount 4, then there's one combination. And then we can look at if you subtract each of those coins. So that would just give us 3. So if we're at 3, so let's instead let's reverse it. So we'll start at our target 4, and then we would subtract 1, 2, and 3. So yeah, we would subtract the coins, and then whenever we get 0, so we'd have 3, 2, 1, and same thing, 1, 2, 3, 1, 2, 3. So I'm just flipping it here. 1, 2, 3. So here we get 0, here we get -1, here we get -2. So obviously we don't want the negatives. This is 1, 0. Here we get 1, 0, -1. And then 1, 2, 3. So here we get 0, -1, -2. And then this gives us 2, 1, 0. This gives us 0, -1, -2. And this gives us 1, 2, 3. 1, 0, -1. And then this gives us 0, -1, -2. All right. Yeah, so there's definitely a lot of repeated work. So for instance, this 1 node, we do a lot of times, right? We do it many times. And it's not as simple as just every time we find a 0, and we can't just store in our cache like, we can't say that, so the number of combinations of, so like the number of combinations at 4 equals the combinations of 3 plus combinations of 2 plus combinations of 1. So this is true, but we could say that if you're at value 1, that there's one combination, I guess. But like I said, this is problematic because you have this path, which is 3, 1, but you also have the 1, 3 path, and that cannot be considered the same. So I mean, what we could do as just like a simple, maybe whenever we find, well, no. I was going to say, so we could find this. So we would find a 0, and then that would answer 1. So we'd say like 0 is one solution, 1 is one solution. And then here we would say, well, we know 1 is one solution, but we have to know if 2, 1, 1 is different from the way that we found it. And to do that, you'd have to go through the whole thing, as opposed to just knowing, like, I can take it or not. So how do you know if you can take it at face value? And then here's another one. So 2 looks like it has 2. It looks like it has 2, which it does. And then could we, so when we get to this 1, would we just say, okay, it equals, so would we say that the combinations at 2 equals the combinations of 1 plus the combinations of 0 plus the combinations of -1, and then this goes to 0, right? Combinations of 0 goes to 1. Combinations of 1 we stored as 1. Yeah. Okay, so I'll just kind of go through with this and see if I get any insights. So here, this is what we have stored so far. And then when we get to 3, we'll say the combinations at 3 equals the combinations of 2 plus combinations of 1 plus combination of 0. So we would say it equals combinations of 2. We look at our table, it's 2. Combinations of 1, we look at our table, and that's, how is that 2? It should just be 1 there. Whoops, my bad. It should be 1. 1 plus combination of 0, which is also 1. So we'd say this is 4. So 3 would be 4. And I think that holds true because if you have a coin 3, you can just do 3. You could do 2, 1. You could do 1, 2. And you could do 1, 1, 1. So we have 2, 1, and then we have 1, 2. Yeah, so this would work. But even if we look at just the case of 3, we see that we have 1, 2, and 2, 1. So we have to store, so it comes down to this, and this is what I've said earlier. We have to store some additional information that lets us know. So maybe we can store 2, 1. Like maybe we can store. Because there's different ways to arrive at 2. Like this 2, there's 2, but we only had this 2 here. Whereas here we got 2 1s. So everything in here should be counted again. So if we just consider the case of 3, we have 1, 2, then we have 2, 1. And in the case of 4, if we look at something like 1, 2, 1, 1, 2, 1, 2, 1 versus 2, 1, 1, those both should not count. Yeah, so I guess I'm a little stumped on what we should. Well, it is 2D dynamic programming, so maybe in our memorization we want to store something else. But it has to also be something that's not just the combination itself, because if we store the combination itself, then that doesn't really save any time at all. I'm pretty sure. Maybe it's like store the combination up until that point. So let's say we were at 3 was our total number, and then we say 2 and 1. So we could store, I guess, that that 2 and 1, and then when we get to 2, 1, we would say that we've already explored that. So that's like 4. Could we cut off? So if we take 1, 2, is that going to have the same result as if we take 2, 1? Yeah, it should. So if we take the same combination different ways, then maybe we should just store that. So instead of storing the value, should we store the combination? Because maybe it actually does make sense. Because if we consider the case of 4 and we have, if we go 1, 2, and next time, like, if we do 2, 1, then we don't have to calculate 2, 1 because we've already. Is that true? Yeah, it should be because we've already ended up in that place with the same combination. So what am I suggesting then programmatically? So should we store, like 3, 1? Equals, so is this what I was saying before? So like 4, I mean, if we have the combination of just 0, then we know that there's one way to get there. If we get to the combination of just 1, then we know there's one way to get there. If we get to the combination of, let's say 3, 1, that is, so maybe it would be, so instead of 1 here, could it be, we're actually storing 0, 1? And then 1, 0, 1, 3 still has one combination. And then we would look at 2, and we'd keep going. Well, we'd have to store, maybe we would just store this. So we would like DFS, keep track of the path the whole way. So we'd say, okay, we're at 3, then we chose a 1, we got a 0. So we'll say that this path, this combination of coins resulted in 1 coin. Let's look at 2. So our first DFS would be 2, 1, 1. So then would we just say 2, 1, 1 results in 1 coin? And then these would result in nothing. So then when we go to just 2, 1, we could say it equals 2, 1, 1 plus another 1 from 2, 2. So then would we say that, so we'd find that 2, 2, okay, wait. So maybe we could say, think about it recursively. So 4 equals, well, I think I was onto something before. Okay, so 2, 1, 1 plus 2, 1, 2 plus 2, 1, 3. So we just have to store these as sorted or somehow. So what does this equal? This is 2, 1, 2, 2, 1. So that's equals 2, 1. So it'd be 1 plus 0 plus 0. So 2, 1, or any combination of, so 1 and 2 or 2 and 1 equals 1. And then we would say that 2 equals 2, 1 plus 2, 2 plus 2, 3, like this. 2, 1 we know is 1. 2, 2 is 1. And 2, 3 is 0. So we'd say that just 2 equals 2. Okay, then we would go to, we'd say that 3, okay. So I think this is the approach. 3 equals 3, 1 plus 3, 2 plus 3, 3. And then, now this is the interesting part. So then when we expand that, so for instance, if we expand 3, 1, we would say that 3, 1 equals 3, 1, 1, 3, 1, 2, and 3, 1, 3. So then we look and see that this has already been explored as 0, so we would just store this in our map. So I don't know if this is enough to just cache it like this, but we could cache the combinations, and then so we would just say that 4 equals 4, 1, 4, 2, and 4, 3. And then we would say, for instance, 4, 1 equals, would it be 4, 1? Or would it be 3, 1? Would it be 3, 1, 2, 2, and 1, 3? And then 3, 1 would be equal to 2, 1, 1 plus 1, 2, 1 plus 0, 3, 1. And this combination would give us, so this is the equivalent in my view of taking, so this is the coin that you take, okay? So this is and this is the remaining value. So then it would be, we took a 1 and then we took a 3. So I don't think you need this value there. So then 3, 1. So what does this 3 even mean? So I said that 2 equals 2, 1, 2, 2, and 2, 3. I guess that's how you would expand it, as you can take, and the base case would be, so 4, I'm trying to think, so 4 would be equal to, okay, so at 4, we could, so this would be our base case, because we're at 4. But I guess alternatively, you could add each type of coin, or in this case, subtract each type of coin, which would be the same as, because that's like -3, -2, -1. And then this would give you 5, 6, and 7, which all of these return 0. But I think we may just be able to say that that's a base case. So should this be 0 or 1? Probably 1. Okay, so this would be, so 2, 1. So that's like what we're at. So if you're at 4, that's like the last thing that we're solving for. So if you have 4, it's going to be equal to the answer. But we can define it in terms of our decisions that we can make. So 2, 1 is here. So do we want to just return 1 plus 2 plus 3, like the combinations? I can't draw. Okay, so is it our target equals all the combinations after you take 1, all the combinations after you take 2, and all the combinations. Okay, and then from each of these, I mean, it's basically, I'm just writing a decision tree, but and then from 1, you could expand that into, we could take another 1, we could take another 2, or we could take another, or we could take a 3. And then because the sum, so are we just going to check the sum of the decisions? That doesn't, I guess for now we can just, so the sum of this is 4. So that means that this combination evaluates to 1 way of summing to our target. And we don't evaluate it anymore. So what I'm thinking is, so then we'd have 1, 1, 1, 1, 1, 2, and then 1, 1, 3. So this evaluates to 5, so this would be 0. This evaluates to 4, so that would be 1. And then here we do another 1, 1, 1, 1, 1, 1, 1, 1. So my point is, we can cache these. So whenever we see any combination of 1, 1, 3 or 3, 1, 1, we can set it to be. So I'm just going to try. Yeah. I mean, I don't, this doesn't feel like the right way, but how I'm going to do it is, basically all I'm going to do is implement the brute force solution, but I'm going to cache the combination that got us here. So in other words, like if we've already calculated 2, 1, and then we try to calculate 1, 2, I'm just going to look at our cache to see what this one was. Like how many did this have? Or should I even calculate it at all? Probably not. Because, so if we've calculated 2, 1, and then 1, 2, we don't want to duplicate anything. So I'll just check if it's in our cache, then don't even like add it at all. So I guess, and the only way I know how to like check this is if we just sort it. So if I store it as sorted, so like every time I look up like 211, I would sort it and say, hey, is 112 in there? I don't know if there's a better way to do that. I mean, I could check like every combination of this. Like, is any combination of this in there? But I think sorting it is faster than that. Okay, yeah, so this doesn't really feel right, but I'm just going to do the brute force and then cache the combinations. And if we've already seen this combination and calculated it and added it to our number of combinations, then we're just going to discard this and not calculate anything at all. So I'll have a set of tuples, I guess, that will be sorted. And we're going to, every time we add something, we're going to have to sort it. So it's, you know. All right, so I'll make a function which I'll call DFS, and it will just kind of go through the decision tree. So we're going to start with DFSing with our amount, I guess, because we're going to start from our amount, and then we're going to subtract it, and then our path, we'll just put in an empty list, and then this will be like the remaining amounts. So I'll just call it remaining, and then our path. And there's no, I mean, we could insert, so we could make sure path is always sorted as we do it, which would be just a linear insertion. Or I suppose maybe we could do that in login, or sorry, just login. Because if we know that something is sorted, inserting it should be login because we can kind of binary search it. I'll just do the sorting way. All right, so for coin in coins, we're going to call it again with remainder minus coin, and then we'll add, so path dot append coin and path dot pop. So we're going to add it and then remove it. So we'll pass path. Yep. All right. So now we're going to check our base cases. So if remainder equals 0, then we're going to so we'll just add, like, we'll have a result. So I'm thinking I can just add a result plus equals 1, and continue. If remainder is less than 0, then we'll just continue. So do nothing, but maybe we should add it to the cache. So I guess what we could say is if sorted path in cache, then just get out because we've already explored it. Otherwise, we'll say cache.add sorted path. So this, I think, is my idea. So we'll have a cache. Yeah, so right now this is working, and then I would return result. So what this does is it's basically just doing the brute force, except if we ever have been down this path before, we are going to exit out, because then I will assume that we've already gotten all the possibilities from this path. So I don't know if this will get TLE or, okay, so what's line 20? I don't think continue is the word I'm looking for. I'm looking for return. Unhashable type list. Yeah, that makes sense. You can sort tuples though, so I think I'll just make it an empty tuple, because tuples are hashable because they're immutable. Now this is a problem. I mean, I could make it a string, I guess. So I could say path plus equal. So let me make it a string. No, I should. All right, so how do we want to store our path? So we could use a string and then sort the string, but I don't think that will work because if we have coins that are with several digits. So I think a tuple makes sense. And then we could just append, so our path would be a tuple, and then we would just add it. So we would say path plus, I don't know how you add to a tuple. Is it just plus? Let me see. So if I have A is an empty tuple, and can I print A plus B? Or is it dot add? Concatenate. Can only concatenate tuple, not string to tuple. So can I make it a tuple like this? Why is that comma there? What if this had C in it? So would this be B and C? All right, so I'll do this again. Probably not the best data structure to do here. So I'm going to create another tuple of just coin. Yeah, so just sorted path. Path should be of type tuple now, though. Why is path a list? We're passing in an empty tuple. Let's see. It's a tuple, unhashable type. Cache is a set. We can have a set of tuples. Yeah, we can have a set of tuples. Maybe sorted assumes that it's a list, so I can say path dot sort. Like this, because tuples are immutable. Tuple has no attribute sort. Yeah, so you can't sort tuples, huh? Tuples are ordered. Can we have a set of sets? You can't sort on a set though. So let me try something. So if I have a set, set 1 equals, let's say AB. Then I have set 2, which equals BA. Does set 1 equal set 2? So I'm guessing it'll say no. It does say true. In that case, could we have a set of sets and then make the path a set? So we could put in an empty set, and then we can, so wait, let me try something. We can have a set of sets, right? So if I have big set equals an empty set, I could say big set dot add a b, right? No, I can't do that. So if we had a list, this would work, but now it's O of n lookup time. So what if I printed is B a in big set? So I'm guessing this was like true. Yeah, so this is kind of the behavior that we want, but the only problem is this list, to look up in a list is O of n. And I'm guessing if we make it a dictionary, it doesn't, I don't think you can have a dictionary of sets. This won't work, I think. Yeah. Okay. You can't have a set of lists either, and you can't sort tuples. Tuples are different though because they have order, right? So if I say that A is a tuple, AB, and B is, I probably should use different. I'll say T2 and T1. So now T2 is BA. And then if I print does T1 equal T2, this will be false, unlike the set. Yeah. Yeah. All right, so I've been at this for 50 minutes. I think what I'm going to do is look at, for even like combination sum or those problems, how you can make sure that the duplicate combination isn't stored. Because before, I think I was just sorting, the combination, which was a list. But I must have had, did I have a set of lists? You can't have a set of lists. So I wonder what I did before. Anyway, yeah, so that was a good little thinking session, I guess. I didn't solve it, obviously, but yeah, I think I'm going to review combination sum because that is something that I wanted to review. I remember I talked about it when I did combination sum. But anyway, thank you guys for watching. Today was day 61 of Coding Every Day, and I'll see you guys tomorrow for day 62.